Welcome. Let me tell you about the linear algebra result which hatched when I was proctoring a 3-hour multivariable calculus exam this Thursday, and it's a result from linear algebra. The name, I will explain the name later, call it the dark matter lemma, but it deals with matrices which come from finite geometries. So here we have an abstract delta set, call this triple an abstract delta set if G is a finite set and D is a symmetric n times n matrix, n elements in this set, and R is a dimension function which tells what the dimension of a specific element is. So this partitions the set into different parts. It gives a notion of a delta set in some cases, which is an important object, but it's more general, and we assume that this L is, when we take the square, d squared, the Laplacian is block diagonal. So this actually follows from the fact that d square is equal to 0, d star square is equal to 0. These are exterior derivatives which define a cochain complex, and so cohomology. So these are the Betti numbers. But we have also this M, and that is important. That's the dark matter part. I discovered this when looking at continuous deformations of the Dirac matrix more than 10 years ago, actually 11 years ago, and it was kind of a little surprise that you have more general matrices which can occur if you make an isospectral deformation. So maybe just as a motivation, there are big ideas in geometry, there are symmetry ideas, like it started maybe with Euclid, who realized that symmetries are important, like congruences or similarities. Klein formalized this in a more concise way and looked at the groups. So group theory became important. Automorphism group of a geometry is important. Emmy Noether was relating this in physics to conservation laws. Einstein also, from the covariance principle, the general covariance principle, the special covariance principle, designed theories which are based on these symmetry ideas. Fond of the maybe less well-known symmetry principle of Arnold. So he kind of noticed that if you take, for example, a free top, can be in arbitrary dimensions, and you let it move. So what it does, it spins around, translates, it spins around. But what it is, it's a geodesic motion in the symmetry group, in this case SON, or the Euclidean group, and you also add rotations. This can go even to infinite dimensions. If you look at fluid dynamics, the Euler equations are actually geodesic flow in infinite dimensional Lie group. That integrable systems we know can be written as a Lux pair, as an isospectral deformation. So what I'm looking at here is also isospectral deformations. If you make the QR decomposition, you get the orthogonal matrix, and you can then take the QT AQ, and this gives you an isospectral matrix. So when you do that with the Dirac matrix, what happens with the Dirac matrix, if you do that and you make an isospectral deformation, even if you start with a no dark matter part here, you will develop this diagonal part. And that also happens, and that's what I just actually only realized this week, also happens in the QR case, which is a discrete time version of this Lux pair. That's something which Symes has realized in the Lux deformation of Jacobi matrices. If you take Jacobi matrices and make an isospectral deformation, you get the total flow. Total flow is a discrete version of the quadratic Vries equation, but if you discretize also time, then you get a QR flow. And so this can be done with any function. Any function produces you a Q, and the nice thing is that this Q then produces, again, a Dirac matrix, and that's the content of this dark matter lemma. It's a lemma from linear algebra, poor linear algebra, but I'm proud about the proof because it is something which is completely non-technical if you are looking at it in the right way, if you define the right algebra. So here is the setup. So first of all, we have to define these matrices, these Dirac matrices. It can be axiomatized, right? What we have is a tridiagonal matrix, D plus D star plus B, where D star and D star, D and B star are nilpotent, so the square is 0. So, and then we have this matrix. This matrix then looks like that. It's 3-block diagonal. And now what we can do is we can define, that's maybe Gon's idea, of a von Neumann algebra. I'm very fond of von Neumann algebras also because this is non-commutative probability theory. C star's algebra, according to Gon, is non-commutative topology, and the spectral triple, which you can look at with the Dirac matrix, is non-commutative differential geometry. So these are grand ideas in geometry, and what you have here is also a matrix algebra. It's actually finite dimensional, so it's a type 1n von Neumann algebra. So it's a very simple von Neumann algebra. The point is that it's just a closed algebra. What we have is if we take these matrices, we multiply them, we add them, and we remain in this class of matrices. Now, it's a little bit more general than just starting with a Dirac matrix and take the functional calculus, define FD. So what we can do is with our functional calculus, we can define FD. And by nature, the FD is again in this form. But if you make the QR decomposition, this Q is not of the form FD for a continuous function. So you are not in a commutative algebra where generated by D. And if you take D and you generate the algebra in all matrices, then it's a commutative algebra. While here we have a non-commutative setup because the Q will not commute with D. Otherwise it would not produce any deformation. So what you have here is, what you can define is, and it's another idea, important idea in physics, and an important idea in quantum field theory and also in geometry. Actually, my geometry teacher was pointing out how important it is to have reflection geometry. It's a very old-fashioned thing, right, from the early 20th century to look at this reflection. Coxeter was especially. So if you look at these matrices here, when you just take one of the columns, what they are actually Coxeter type, they are kind of produce you 0 when you take so it's kind of like creation operators in quantum field theory. But what you have is if you define the algebra just as an algebraist, you can define the algebra generated by these matrices given the D. You start with D, you get these matrices, you produce the algebra, you get a non-commutative algebra. But what happens, it's all these matrices which you get are still in this tri-diagonal form. So now, and that's kind of where now Gram-Schmidt comes in. If you take such an element and you do Gram-Schmidt, Gram-Schmidt is a beautiful thing. It's one of the 10, top algorithms in all of mathematics. It's very important, and it's a crime to leave it out in a linear algebra course. Here I made once a song about this. I'm dancing right beside you. There's nothing wrong. Just to make you feel fine. We were Gram-Schmitting all night long, so that's the key. You're Gram-Schmitting for the QR decomposition. This is equivalent, right? It's an equivalent picture. So you get this Q by doing Gram-Schmidt on the columns of the matrix. So you orthonormalize these columns. It's one of the very important principles based on Fourier theory. So it's also one of the great ideas in geometry. That's why it belongs to the 10 most important algorithms. I saw that once in a list of 10 most important. I don't agree with all. I have to make once a video about this, but it's definitely one of the 10 most important algorithms in all of mathematics. The QR, it can be used to invert the matrix simply. It can be used to diagonalize the matrix. But it's not only that, it's the process of producing an orthonormal set. That's very important in mathematics. So you have an orthonormal set and you can work much nicer. You have a coordinate system which is much nicer. It's nice to have a coordinate system which is orthogonal. So it's harder to work in a coordinate system which is not orthogonal. Even in general relativity, this is used. You use orthonormal frames. So that's one of the important ideas in mathematics. And so what you do is you can just look what happens if you do Gram-Schmidt. I was Gram-Schmitting also, as you know, all night. It's a frustrating process because you have a lot of work to do, but it's what happens is you end up here with whenever you do a step, Gram-Schmidt step, you subtract something which you have done before, a multiple of what you have done before, or you scale, you stay in this algebra. It's also Q is in this algebra. And then also D has the same form. I'm not yet sure whether it's in the algebra, but the R is definitely in the, upper, it's definitely upper tri-diagonal. So there's only upper diagonal part and the diagonal part. It's actually tri-diagonal. The R is upper tri. The R is upper diagonal. So that's the thing. Maybe I just should say something about the name of why dark matter. I was very excited here, so it was not well received. So this idea that you actually, because it's a little bit crazy, like Zwicky's ideas are crazy. Fritz Zwicky is kind of he's a Swiss now. He came from Switzerland and went to Caltech like me, and he's also a little bit crazy or bold, like I sometimes am. And so Zwicky, I'm a big fan of Fritz Zwicky. So he suggested from data, of course, not just speculation. He suggested from when looking at data that there must be something like a dark energy or dark matter, which is in the universe to explain the data, and that's still not solved. We don't know what the dark energy or dark matter is. Is it tiny black holes, or is it some new type of matter, or whatever it is? So from a pure mathematician point of view, what happens if you look at the geometry, like this is a very general class of geometries, simplicia complexes or whatever you look at, delta sets are part of that. And you start with that and you just let it flow. Just let it go freely in the isospectral set. So you consider this isospectral set as your symmetry group. So you can deform you can make this into a framework, like a category, and kind of define what you actually do with this. It's a chain homotopies, and so you can actually consider this as morphisms. So in some sense, what you're looking at all the, you look at the equivalence class of all the possible geometries, which can be obtained by just letting the geometry freely evolve, like a free body, like a stone in space. In space, it will just move and turn. And the probability that it doesn't move and doesn't turn is 0. So it will move with probability 1, or any system which you look at will evolve in the isospectral set. You can consider this this Arnold principle. And so when that happens, there is something interesting happening, namely that you have a separation of this D and D star, which is the kind of the electromagnetic part, because it is entering for example, the Maxwell equations, or also, non-commutative versions like some Alonzo-Klein systems or whatever you're looking at. It always involves the exterior derivative. And then there is a new part which grows, the m here, the m grows in, the m grows when you are looking at it. This is not yet proven here. I see this experimentally. Maybe I show an experiment here. Here is I took a random graph. It's simplicity complex. Then I produce the Dirac matrix and I deform it using just f of v is just the e to the t. I take the heat. You can take the heat or the cosine dt. So there are lots of interesting cases, which this is the wave operator, this is the heat operator. You can take this, for example, just has to be invertible so that you have no numerical instability. Dealing with the kernel is more subtle, so that's why we assume that it's invertible. Is going to a block diagonal, dt becomes almost block diagonal, which means that the dt shrinks. But if the dt shrinks by Gahn's formula, gradient shrinks, right? If the operator, the gradient shrinks, this means actually space expands. And also you see inflation. You see something initially very large expansion, and you have this inflation part, which is not just some Deus ex machina principle which you postulate, it is a mathematical necessity in the symmetry group of a geometry. Which is really, really exciting that you have this, whether this is has to do with physics or cosmology is pure speculation, but this is mathematics. It's linear algebra. That's it for today.